Hello and welcome to MT3. We are now on our last topic of this kind of course, partial differential equations or PDEs, and I will be following Riley, Hobson and Benz chapters 20 and 21 here, and Arfken, Webb and Harris chapter 9. I will be paying particular attention to Arfken's book because some of the issues in most of the issues are, topics are covered quite nicely in Riley's book, particularly in chapter 21. But in chapter 20, there are some things which are not explained as clearly as they should have been. Okay. Also, Arfken's treatment in chapter 9 is a very good first introduction. It covers most of the important topics needed for a physics degree. And Riley's book takes you into some more detail into some interesting things, but not always explained with clearly enough. Okay, so why are we interested in partial differential equations? Well, a short answer is that we live in a multidimensional world. So the differential equations which govern our physical laws are multidimensional, and therefore we encounter the partial differential. For example, the wave equation shown over here involves three spatial dimensions. So this Laplacian over here, three spatial dimensions, x, y, and z, or you can go into different coordinate systems, and it also involves the time derivative. So we've got four dimensions in this Laplacian in the wave equation. What does the wave equation describe? It describes the solution u of r and time describes displacements from equilibrium at position r and at time t. So this could be the oscillations on a string that would be one dimension in space and one dimension in time, or it could be the oscillations in a drum membrane that would be two dimensions in space and one dimension in time, or oscillations in a medium, three-dimensional medium, in which case you have three dimensions in space and one dimension in time. And here this constant c is not the speed of light, it's the speed of the wave. Okay. Right, so this is described in Riley, Hobson and Benz 20.1.1, and I've given you an illustration here of what u means in one dimension in space. Then we have equations like the diffusion equation, where now we've got some constant kappa multiplying the Laplacian, and we have a single derivative, a first order derivative in time, unlike the wave equation where this was a second order in time. Here the solution u of r and time describes the pressure or the concentration at a particular position in space and at a particular time. And this equation is valid in a region without sources or sinks. So you don't have a source of perfume, or you don't have a sink, meaning something is being extracted from the medium in some way. Alright, the diffusion constant is where the physics lies. So if you wanted to know exactly how fast a molecule propagated in air through a random walk, well, that's encapsulated in the kappa here, and that's a single constant. It's quite remarkable that equations like these, often depend on just one or two constants, and they describe the fundamental phenomena they're trying to describe are actually quite complex. Then you've got Laplace's equation, which you should have seen if you've done Maxwell's equation. Here u is, there's no time the derivative here, and here u is the steady state temperature concentration. So you could look at this as a special case of the diffusion equation where we are looking at a phenomenon which is now time independent. Okay, and this could also be the electrostatic potential in the region without charges, or the gravitational potential in a region without matter. Now, if you do include charges or matter, then you need to include a source function, and that's the rho here. So this is simply the Laplace's equation, now with a source function rho, and this is the Poisson equation. So this is, as I said, this is Laplace's equation for a system containing a source. And this could be the charge density, in which case you would get the electrostatic potential. And here epsilon naught is the permittivity of free space. All right, and this is going to be quite an important equation to be able to solve in electromagnetic theory and in Newton's theory of gravitation. Now here's an equation which you are all familiar with, the Schrödinger equation. Now let's see, this looks like it has elements of both the Poisson equation and the diffusion equation. We've got a single time derivative here, we've got the Laplacian here, and we've got this potential here. Three things in here. And here the wave function is a function of position and time. Of course, this is the wave function for a single particle. If you have multiple particles, multiple electrons, this all gets much more complicated. Okay. So we need to solve these kinds of equations, and we're going to start simple. We're going to start with, first of all, what are the differences between a partial differential equation and an ordinary differential equation. Let's start with an ordinary differential equation you have seen now quite often. dp by dt is equal to lambda times p. That means the rate of change of p is proportional to p itself, and the proportionality constant is lambda. And we have a single boundary condition that p at time t is equal to 0 is some constant p naught. We know the solutions. These are of the form a constant c times e to the lambda t. And from the boundary conditions, it's easy to show, in fact trivial to show, that c is equal to p naught. So the full solution then is p of t is this constant p naught times e to the lambda t. Now if we consider the analogous partial differential equation, it would be the partial of p with respect to t is equal to lambda times p, and here p is understood, let's say in this case, to be a function of space, x, and time. And we have a boundary condition, but this time the boundary condition is not that p is equal to time t equal to 0, p is equal to p naught, constant. Instead here, at time t is equal to 0, p is a function of x. So it's a function of x only. We give it some initial condition. But this initial condition is provided on an entire section of the space. If you regard this as a two-dimensional space, then here we have got p specified as the function p naught on a line in this space. And the solution once again is p of x comma t is a constant times e to the lambda t, but here the constant is not a constant in both variables x and time. It's a constant in x. So what I mean by a constant, I mean as far as time is concerned, this is a constant. As far as the time coordinate is concerned, the partial with respect to time doesn't treats any function of x as a constant. So so here the c is not a scalar; it's a function of x. And you can try this out. You can plug this function into this equation here, and you'll see that it does satisfy this equation. So now we need to apply a boundary condition, and the boundary condition is that at time t is equal to 0, so this is when the exponential is 1, then p of x comma 0 is equal to p naught. Therefore, this constant, this function c of x is equal to p naught of x. And the full solution then is of this form. Yeah. So you can see what's happened here. Let's just summarize. Where we had constants, we now have functions of the other variables. Where we had boundary conditions specified at particular points, we now have boundary conditions specified on surfaces or lines. Yeah, and this is something we're going to see often in when solving partial differential equations. Another thing to consider here is that if I hadn't specified any boundary conditions, then all you would have been able to say was that the solution is of this form, where c is any function of x, sine of x, cosine of x, tangent of x, e to the x, sine hyperbolic of x, it doesn't matter. Any function of x would have worked here. Now this is quite different from what you've been accustomed to in ordinary differential equations, where at the most you had some scalar numbers which were undetermined. Here you've got entire functions that are undetermined, that become our effective constants, And this gives partial differential equations much more flexibility in describing in the solutions. Now let's have a look at a particular class of partial differential equations which we will find quite useful, and these are described in Arfken, Weber and Harris chapter 9. In fact, we are in section 9.2 at present. So here we have a linear operator L, which is defined on its action on phi. Phi is a function of x and y, and this is given by some constant b, and you have the partial of phi with respect to x and the partial of phi with respect to y. So a times the partial of phi with respect to x plus b times the partial of phi with respect to y is 0. And we need to solve this. Now, a powerful way of solving this is to, quite useful way I would say, is to change variables. And we'll see how this works, and then we'll try and motivate why it works. So we change variables from x and y, phi is a function of x and y, to s and t, where s and t are given as follows. S is ax plus by, it keeps the same form as this equation, and t is bx minus ay. Now, if I asked you to plot these as these are lines, right? And you will see if you made a plot that the t lines are orthogonal to the s lines. So what we have then is s is a function, could be treated as a function of x and y, and t is a function of x and y given like this. And likewise, if I invert these equations, you can write x as a function of s and t, and y as a function of s and t. Try it out, try and make the inverse and find out what these functions are. Now what we want to do is to take this the starting differential equation, which is written in partials with respect to x and with respect to y, and write them in terms of partials with respect to s and t. So we use the chain rule here. The partial with respect to x is the partial of, since x is a function of s and t, it's the partial of s with respect to x times partial with respect to s, plus the partial of t with respect to x times the partial with respect to t. And if you look at the expression here for s, we get a times partial with respect to s plus b times the partial with respect to t. Likewise for y, this is given by b times the partial with respect to s minus a times the partial with respect to t. Now if you're unsure about these the chain rule, it's basic, the basic chain rule from differentiation. Please just look it over and make sure you followed what's happened here. Now what we're going to do then is to say, we started off with a function phi, which is a function of x and y, but x and y themselves are functions of s and t, so we're going to substitute those functions in here, and then you could regard the phi as a function of s and t directly. Now it's the same function phi in all cases, it's expressed in different variables, but in order to just remind ourselves that we have done a transformation of the coordinates here, we'll put a little hat there. That's all that we are indicating, right? The hat is just as a mnemonic for ourselves. So that we can start with our partial differential equation. So 0 is equal to a partial phi with respect to x plus b partial phi with respect to y. We put in these new expressions for the partial of with respect to x and the partial with respect to y, and what we end up with is a squared partial of phi hat with respect to x, and then you have cross terms, and then you have b squared partial of phi with hat with respect to s. This should be, yes, that's correct. And the cross terms, which involve the partial with respect to t, they cancel out. And what we're left with then is a squared plus b squared times the partial of phi hat with respect to s. Now this is cool because what we've done is we've taken a partial differential equation which involved partials with respect to both coordinates, and now we're left with just one coordinate in there, and this is easy to solve. What we've done is taken a partial differential equation and converted it into an effective ordinary differential equation, and we know how to solve ordinary differential equations, and that's the power of this technique. So as long as a squared plus b squared is not 0, and if you think about it, if it was 0, then what would happen? Just try and figure it out. Then we must have the partial of phi hat with respect to s is 0, which means that phi hat is a constant as far as s is concerned, which is that it's a function of t alone. Okay, so phi hat is some function f of t. Now we can go back to the original coordinates, and we can write this as in terms of x and y. That gives us phi of x and y is equal to f, that same function, where t is now substituted in here. So now we have a f is a function of bx minus ay in that order. So f could be the sine of bx minus ay, or the cosine of bx minus ay, or anything you can think of, but you will always find x and y appearing in this form, and that's what's important here. Okay, so what we have shown, and this is quite a beautiful proof actually, is that this solution to this particular equation is always of this form. We don't know what the function f is. It's anything, but it's like this. Now how would we find out what f is? We'd need the boundary conditions. We haven't got them here, so this is as far as you can go. Now we can take this a step forward. First of all, why have we done this? Well, these expressions, so s is equal to ax plus by, are called the characteristics of this equation. Remember, s, the choice of s, it kind of mirrored the structure of this linear operator L. The linear operator L was given by a times d by dx of phi plus b times d by dy of phi. And our choice of s was a times x plus b times y is equal to s. That's called the characteristic. Now why? Let's see what this means. So these are lines. I've said it before. I mean, these are straight lines. For a given s, this is a straight line. So we plot them here. This is x and y are our coordinate system, and for a given s, we have a straight line. And there are an infinite number of these straight lines. The t's are orthogonal to the s's. So if you have a given t, then you'll have a function, a straight line going perpendicular to the ones, the s lines. Now, phi is a constant along the s direction. We had d phi hat by ds was 0, which means there is no change of phi along one of these s lines. And it's as if, so the only change of phi is orthogonal to these s lines. And this is why phi turns out to be a function of t. We say that. And one way of thinking about this is that, once you've got phi along these lines, you can propagate it along the t direction. It changes along the t direction. And these s lines, which in this case are just lines, are characteristics of this partial differential equation. Now the whole idea of characteristics is much more complex and rich than what I'm showing you here, and I will provide links to some very useful YouTube videos which show you how to generalize this idea to much more complicated partial differential equations. This is also done in Arfkin's book and to a larger extent in Riley's book. But the treatment in Riley's book might seem a little bit confusing if you read it. Arfkin is somewhat clearer. Another way of looking at this whole idea of characteristics is to look at take the partial differential equation we had, L operating on phi is 0, which is written down here, and then write it in terms of vectors. So I can pull these two constants out. By the way, these need not be constants in this is what Riley tries to show you, is that this could be a and b could be functions of x and y themselves. But the point is you can pull them out as a two-dimensional vector, and then you have this is of course a transpose of a vector, and then you have the partial of phi with respect to x and the partial of phi with respect to y forming the other vector, and this is of course the gradient vector. So then if I define this to be the vector v, then we have v times the gradient of phi is 0. The gradient of phi is 0. Now what this is called the directional derivative. It's the derivative of phi along the direction given by this vector v. And what we are saying is that this directional derivative of phi is 0, which means phi does not change along this direction. It must change along a direction orthogonal to this. And this is why phi turns out to be a function of the coordinate t. The nice part with this approach is then you can take a more complex form of this vector v, which depends on x and y itself. Not here we had a constant a and b. They could be functions of x and y, and then you have directional derivatives, which actually are much more interesting. But I won't say more about that here. You can find out more about this topic in the additional resources I will provide, and done by people on YouTube. So brilliant. Okay. Now let's have a look at the more complex example. This is also in Arfkin's book if you want to have a look there. So here we've got the partial differential equation, d phi by dx plus d phi by dy plus x plus y times phi is 0. And what we're going to do is to examine the part which contains the derivatives and convert that part into a single differential using this change of coordinates. And then we will have a differential equation in that single variable. So here, if you compare this to what the equation we had before, a is 1, that's a is the coefficient of the partial with respect to x, and b, the other coefficient, is also 1. So our change of coordinates should be s is equal to x plus y and t is equal to x minus y. We insert this into the above equation, and please show this. You should be able to show quite easily that you end up with 2 times the partial of phi hat. Remember, phi hat is a function of s and t. 2 times the partial of phi hat with respect to s plus s times phi hat is 0. This is the linear equation which can be solved quite easily, and you end up with the solution. Phi hat of s and t is the exponential of some function of t times e to the minus s squared over 4. Now where does this function of t come in from? It comes in from this thing which would have normally in a normal ODE, this would have been a constant, a scalar, but here it's not a constant, it's just a function of the other variables. Here we are integrating over s, so this constant is not a constant, it's a function of t, the other variable. Alright, so we can write e to the ct as some function f of t, so the general solution then is given by some function f of t, which we do not know what it is, times this exponential of e to the minus s squared over 4. And we can go back into the x and y coordinates to write phi as a function of x and y is given by this function of x minus y, t is x minus y, and times this exponential of minus x plus y squared divided by 4. You know, cool, right? I mean, this is one quite neat way of solving partial differential equations. And it can even be used for solving certain kinds of second order partial differential equations. Now once again, just to remind ourselves, we have a function which appears in here, a function of x minus y, which is unknown. All we know is that it depends on x and y in this particular way. We don't know anything else about it. So how can this be used to solve more interesting equations? And this is a second order partial differential equation of the form a squared d squared phi by dx squared minus c squared d squared phi by dy squared is 0. Now this can be factorized, and that's what's important here. It can be factorized into a d by dx plus c d by dy. That's one operator, call it L1. And then we have another operator, a d by dx minus c d by dy, and that's L2. These two operate on phi to give you 0. Please check this. Also verify that these two operators commute. So L1, L2 minus L2, L1 is 0. In other words, the commutator bracket of L1 and L2 is 0. Therefore, the order in which you apply L1 and L2 does not matter. And what that means then, quite conveniently, is that solutions to this equation here can be obtained by either requiring L1 operates on phi to give you 0, in which case a d phi by dx plus c d phi by dy is 0, which is what we've already solved, or require that L2 operating on phi gives you 0, in which case we get a d phi by dx minus c d phi by dy is 0. And you know, the solution to this follows exactly along the same lines as the solution to this. So the first equation we've already seen has solutions of the form some function f of cx minus ay, c times x minus a times y. And the second equation will have solutions which are of the form, I've called it g prime, of minus c times x minus a times y. Now, please convince yourself that these are exactly the forms of the solution for these two equations. Now what we can do is pull out these two minus signs, this is why I had the prime here, and just call this a function of g of cx plus ay. So in general, the solutions to this second order partial differential equation here are given by as the sum of two kinds of functions, f of cx minus ay plus g of cx plus ay. Now why is this important? Because one of our kind of physical equations is the wave equation. And if you're looking at the wave equation in the 1 plus 1 dimension, where I mean one spatial dimension and one time dimension, then this equation is of the form given above. It's of this particular form. So we can use these ideas now to write down our solutions to the wave equation. And we put it into the form we had above, and this gives us our solutions psi of x and t as some function f of x minus ct plus some function g of x plus ct. Now this thing here, if you increase time, you can see that this is a wave propagating along the positive x direction. It's going towards larger values of x, because as time increases this number gets more and more negative, so this has to get more and more positive for the center of this function to be the same. So effectively it's moving that way, and likewise this function g of x plus ct moves in the opposite direction. So our solutions to the wave equation are exactly what we kind of imagined them to be. It's combinations of waves moving left and right. We don't know what these functions are. They will depend on our initial conditions and our boundary conditions, but what we can say is that they must be of this form. This is pretty cool. Now Arfken generalizes this to look at more complex forms of this kind of solution, and I do require you to read Arfken. Riley, Hobson, and Benz is a little bit optional here. It has nice examples, so please read them for the examples and work through those. But Arfken is the bare minimum of what you need to be looking at for this topic. Chapter 9 in Arfken. Now, finding the characteristics of an equation can be a powerful technique. It has been used. You can find out beautiful aspects of the solutions using these techniques, but quite often it's not really the way you want to find the solutions, because quite often our boundary conditions and even our partial differential equations, our source functions, might be too complicated to use in a solution using the method of characteristics. Instead, we find the method of separation of variables to be one of the really powerful techniques which you will find useful in almost every branch of physics and engineering for that matter. And the idea here is quite simple. If we have a function, if our solution is a function of x and t, let's make an ansatz that it's some function of x times some function of t. Now you might say, surely this is too restrictive, and you're right, it is. But under certain conditions, what we will find is that even if we can't represent a function exactly as a single function of x times a single function of t, we will be able to represent it as a sum of such products x and t. But for now, let's accept this and see what happens. So here, just to illustrate the idea, let's use this on our differential equation, which we have already solved. We know what the answer to this looks like. Okay, so the idea here is we have a partial with respect to x and a partial with respect to t. Let's evaluate these partials. So the partial of phi with respect to x is the partial of partial of capital X, capital T with respect to little x. Now there's just to keep you alert here, capital X is the function of little x. Capital T is the function of little t. Now sometimes my handwriting hasn't been that clear, but here, the littler one is the variable and the big one is the function. Now, the partial with respect to x ignores the t, so that just comes out, and then we are left with the total derivative of x with respect to little x. It's a total derivative because capital X depends only on little x. So it's no longer a partial here. Similarly, for the partial of phi with respect to little t, this becomes capital X times the total derivative of capital T with respect to little t. Now we insert these into our PDE, and we get the following equation here. Now we're going to divide by phi, which is xt. If we divide by xt, what you end up with is a times 1 over x times dx by d little x plus b times 1 over t times dt by d little t, and that's 0. In other words, a times x prime over x, I've just called these derivatives with the prime, that's equal to minus b times t prime over t. Now what we've got here is, on the left hand side, is something which is a function of little x only. There is no time aspect to the left hand side. On the other hand, on the right hand side, we've got something which depends only on time, on t only. Now the only way for these two to be equal to each other for any x and any time is that they are both a constant, a scalar, a constant that is independent of x and t. So we've called it k. So the left hand side is equal to the right hand side is equal to little k. And that gives us two ordinary differential equations. So now we have one ODE for x and one ODE for time. These can be solved quite easily, and you have your, assuming, well, this is right, I haven't decided what k is it positive, negative, imaginary, we haven't said anything, but it's going to be, the solutions will be of this form. X as a function of little x is some scalar cx times kx over a, and similarly for t, it's kt over e to the k minus kt over b. You can put these two together, combine those two scalars to give you another scalar here, and what we then have is our solutions are of the form scalar times e to the k over ab times bx minus at. In other words, it's c times a function of bx minus at, which is what we had before, except for one thing. What we have got here is that this function is of the form an exponential of a constant times bx minus at. So we have got a function of bx minus at exactly as we got from the method of characteristics, but it's a particular kind of function, it's just the exponential. While earlier we concluded that it could be any function f. So how do we reconcile these two? Okay, so this, the idea here is that this particular function of x, first of all, k could be imaginary, it could be real, it could be positive, negative, it could be anything. And if you take the case where k is imaginary, and we'll see examples of how this happens later, then what we will get is a complex exponential. Now, if you then remember what I said that although we will assume in this case that phi is a single x, function x of x times t of t, in general this will be a linear combination of such products. And what we're going to see soon is that in general phi here will be a linear combination of these kinds of exponentials or complex exponentials, and from those linear combinations we will use those as a basis to represent any function f as of x and t in this particular form. So there's no contradiction here, just that we haven't solved the entire problem yet. Okay? Okay. And I've said this out in words here. So it's once we apply the boundary conditions and initial conditions, we see that we can form linear combinations of any, which give us any function f of bx minus at. So I hope I've convinced you that you can use the method of characteristics. It gives you solutions, it tells you the form of the solutions, and we can use this technique called separation of variables, which gives you the same kinds of solutions. Now, in the remainder of this course, we will look at the method of separation of variables. So more on that coming up soon. Thanks for watching.